Okay, so this is a video about the chain rule. The idea here is that one of the easy ways to deal with more and more complex functions and their derivatives is to actually break them down into simpler functions. And sometimes that can be done by looking at them as products or quotients, or looking at them as sums or differences. But another way that we can break them down sometimes is using what's called decomposing them, or taking what is a composition of functions and kind of seeing it as two separate pieces. So in the chain rule, you start with a function, we'll call it capital F, which is a composition of two other functions, and f and g have to be both differentiable. So you have to have a derivative at whatever point that you're trying to do this at. Okay, so if that's the case, then f prime of x is going to be little f prime of g of x. So note, the f gets the derivative, but the g does not. And then we're actually going to multiply that by the derivative of g at x. So it's like you take the derivative of the outside function and keep the inside function, and then you multiply that by the derivative of the inside function. This is the same as, okay, so if you have dy dx, so that's the derivative of y with respect to x, that is the same as the derivative of y with respect to u times the derivative of u with respect to x. So you can see kind of like y as something that's eating u. You take the derivative of y with respect to that, and then take the derivative of u with respect to x. And I think this is actually a little bit easier to see like the mathematics of, because like it's just really simple to visualize like the du's canceling and see, oh yeah, that kind of makes sense. That's not exactly what's going on there, but it does make kind of an analytic sense. So let's look at a couple of examples. Okay, we're actually going to look at the same example posed two different ways. Okay, so let's say f of x is equal to 3 times the quantity 2x minus 1 squared. Now, you could expand and then simplify this, but in actuality, the chain rule makes this a little bit easier to work with. According to the chain rule, my outside function is 3 times something squared. So if we just had that, we would take that power, multiply it by the coefficient, which gives me 6, leaving the inside alone, and then bring that power down, which would be 1, right? So it'd be like 6 times 2x to the minus 1. But the chain rule says I have to look at this inside function, and I have to take its derivative and multiply by that. Well, the derivative of 2x minus 1 is 2, and I can simplify this to like 12 times 2x minus 1. If I wanted to, I probably could make it 24x minus 12. So this is what the derivative is, okay? So pretty straightforward, not too much. If you actually did the multiplication and expansion here, you would end up with the same answer. Okay, so let's frame the same problem slightly differently. Let's let y be 3u squared. Okay, so that's the outside function. Take 3 times u times something and square it, right? Square the something and multiply it by 3. And then let's let u be equal to 2x minus 1. Well, that's my inside function, right? So if I compose these, I would get, like, if I put these all together, I'm going to get f of x up here. So let's take the derivative of y with respect to x. Well, that should be, well, let's see, that should be dy du times du dx, right? But we know here that dy du, well, that's going to be, let's see, 2 times 3 is 6 u to the first, right? It's a little like 1 there-ish. And then du dx is just going to be, let's see, well, the derivative of 2x is 2. and that's 0, so it's 2, right? So this should be 6u times 2. Okay, well that's 12u. But wait, we know what u is. U is 2x minus 1. So this is 12 times 2x minus 1, and lo and behold, we get back 24x minus 12. Same answer. So these are just like two different ways of considering the chain rule here, right? One is to see it as derivative of the outside function of the inside function times the derivative of the inside function, or just dy dx is dy over du times du dx. So there's our game.